Excellent. Good evening. Welcome to the Grasshopper user group meeting. We have a group here for you. I'm Paul from Simply Rhino. I think you all know that Simply Rhino supply Rhino support and associated training services here in the UK. I just want to say a few things. Now, we're going to have presentations from Sam from Eckersley O'Callaghan, thanks for the wave, and which will be followed by some questions and some discussion. And then we're going to hear from Clemens, who is the developer of Karamba3D, known, I think, to quite a few of you in the audience. Also, we're happy to have a kind of guest panelist with us also, Jeroen, who Jeroen's from Thornton Tomasetti, the core studio team that's growing team in London. Jeroen has an announcement for us that he's going to make in between the two presentations about an interesting event that I'm sure some of you are going to be interested in hearing about. So we'll hear more about that from him a bit later on. But yes, so a couple of other notes. It's being recorded, of course, as usual, and you'll find all the recordings of the previous events on our YouTube channel and on rhino3d.co.uk. We're holding these events, and there tend to be three streams for these events. There's the general Rhino stream, there's a Grasshopper stream, and also AR/VR, which we've held a few of those meetings recently. But I think we're going to hold a few more with a Grasshopper and some Rhino focused events over the next few of the iterations of these meetings. Okay, so just a note on questions, and I'm going to hand over to Sam in a moment. Please type questions in. You know, more questions the merrier. So please, questions are very welcome. We do also have the possibility of turning people's mics on. So if there's a burning question that you'd really like to have a discussion with Sam or Clemens or any of us, you know, you're very welcome to do so, and we'd like to encourage that. So please just make it known that you'd like to have a discussion with anybody, and we'll make that possible. So other than that, I should have also introduced Steph, who's here and helps organize these events. Be wondering who that was also. So thanks, Steph. Other than that, I'm going to hand over to Sam now. So Sam, your presentation is up, and we'll all be back with you after your presentation for the questions. So thank you.
Okay, so EOC, structures and facade engineers. I dabble a little bit in both, although my background mainly in structures. We have 8 offices around the world, done projects everywhere, pretty much. In fact, I've only had one project in London in the last, or one project in the UK in the last 6 years. Which is the one on the bottom left, which is the Sky Pool in London, which will be opening later this year, hopefully. No, it will be. So I'm very much excited about that. We're best known for our Apple stores, especially the glass. So top left, bottom right are Central World and Marina Bay Sands at Singapore. And we've started to do a little bit of super yachts and cruise ships. So on the top right is a glass staircase that I worked on a super yacht by Benetti in Italy. I'm going to talk about favorite algorithms, my favorite algorithms, starting with k-means. So k-means is a clustering algorithm of which there are many. So there's a list of a few there, and what I'm mainly used k-means for is geometry rationalization. So I'm going to touch on that. So here's an image of some panel clustering. This is kind of you might have seen this kind of thing before in relation to k-means. So basically the idea is to see, try and rationalize the number of panels, reduce the number of panels, and thereby hopefully save cost and logistics on site and that kind of thing. So just going to go through the kind of problem, which sounds very simple, but is actually quite hard to do. So the problem is, how do you group a number of objects into k groups, where k is the number of groups? So this is how the algorithm works. Say we want 4 groups. This is the basic vanilla version. You pick 4 items. You assign the groups based on their the closest item to each one, and then you move that original point into the mean of those groups, and repeat. So you'll see as we kind of progress through here, the points get reassigned to their closest center mean, and then the points move to the center of those objects, and we kind of iterate until we converge. So it's a nice simple algorithm, which is kind of why I like it. I'm a simple person, and it seems to work quite well. So there's our kind of output. So when it comes to panels, first thing we've got to kind of figure out is, how do we measure the distance between 2 panels? It's quite easy to understand how you'd measure distance between points in space, but with panels, how do we measure their similarity or difference? So 2 panels will be the same, triangular panels, if their edge lengths are the same. So one easy way to measure the distance is by this formula here. One thing we just got to be careful about is the orientation. What happens if it's rotated and therefore there's not an alignment with the sides? Well, we've got to measure it 3 times and take the minimum. Some other things to consider are, what are we allowed to flip panels, and then there's some other considerations when we go to higher polygons, quadrilaterals, etc. So this is kind of what it looks like in our Grasshopper environment. We've got our edge lengths here. We stick it into our clustering algorithm, tell it whether we're allowed to flip or not, and it spits out our clustered objects and our panel shift and panel flip parameters. So it's a little bit more complicated than that, as you could well imagine. We've got our groupings, but then that doesn't mean that they're all identical. So we kind of create an average and then replace our panels in their kind of original position. So here's a little kind of study we did for a Star Pavilion, and we're kind of looking at how the K, the number of groups, affects the deviation of each of these panels, basically the gaps that we'd need between them. In the end, the client decided that he was very much keen on having as few panels as possible, and didn't really care about the gap, as it was a rain screen system, and we were fine with 1 in the end. But it was interesting to do this study, looking at how that changed. Now, in this study that I did recently for a project, we had a more kind of free form. The architecture was a lot more free form, which meant we were kind of more able to play with the geometry. So here I'm using kangaroo in the background and kind of clustering, and then kind of smoothing the structure to fit the clusters and repeating. So there's a bit of kangaroo play there to kind of, you can see the deviations coming down to about 3 millimeters for 10 different panels. So a few things to kind of consider. One, about the algorithm side of things. What is K? How many panels do we want? And as you can see, you can kind of play about and see what the deviation is. Another thing to consider is how you measure distance. I've explained about triangles, but you might be comparing other things, not just panels, but any sort of geometry, and there might be some normalization needed. But other things that are really important that I kind of want to stress is the other side of things to consider, which are like what is the tangible benefit you're getting? Because it's nice to kind of think that if we make many panels the same, then everyone will be happy, but you might just be simplifying one part of the process and kind of adding complexity in other parts. So, you know, what tolerances are acceptable? And in these two questions, you really need to think about the details. How's it manufactured? How's it installed? It really depends on the system. Have we got an open joint rain screen cladding system where the joints are allowed to be large, or have we got some toggle fittings or clamp detail where really we're only talking about a handful of millimeters that's acceptable? So some kind of interesting thought that needs to go behind these as well. This was a cruise ship project. What was interesting here is other ways of tackling this problem. We're kind of using normal kind of geometry like a torus here. So Martin Francis, the designer, chose a kind of torus layout to get a high level of repetition. So not using clustering panels, but the reason I bring this up is because at the end of the day, the contractor was like, well, I don't mind, I'm cutting these panels with machines and it's all going to be automated, and he kind of smoothed things, changed things around as he wanted. So it was a kind of interesting thing to note that, you know, it's not always of benefit to do these things, so that kind of needs to be considered. And here I just want to show properties. So on the left, I've got a nicely optimized structure. This is a pavilion structure which is glazed with glass. I've optimized it. Every beam size is as optimal as it can be for stresses and deflections, but it's not very buildable. So one kind of nice way of using k-means is kind of reducing the number of properties here, and then you've got the rationalized element on model on the right, where we've only got 5 properties down from 30. And I find this quite nice visual to demonstrate kind of what happens when you reduce the number of sections, which is on the x-axis, what happens to the weight of the structure. So you can see here it really starts to spike when we reduce it further below 5. So that was chosen as our kind of nice stopping point. So a nice balance between steel savings, but kind of making it easy to fabricate. So my next one is SIMP, or solid isotropic microstructure with penalization. So you might not know the name, but this is a topology optimization algorithm. Clemens might talk about BSO. I know that that's in his Karamba software, but SIMP is another popular method. You will have seen things like this. So it's kind of topology optimization, putting structure where it's needed, basically. One thing that I wanted to kind of just highlight is that you will have seen this before as well, probably. Gaudi's hanging chain models, that inspired this. It's got nothing to do with SIMP, but my point is we end up with this inspired from the hanging chain models, not this. It's inspiration. I think people take these things as too literally, and I think what I want to get across is that you can use them to inspire and also to understand. So here's kind of a dome for a different cruise ship project, and here we can see we're minimizing strain energy, which is a kind of a measure of how well it's working, with some constraints there. And what's quite nice is that it gives us a little bit of understanding of the structure. So at the top here, we've got a two-way spanning structure because it's quite flat. Then we've got more or less columns at the side, and then where it kind of bows round, we've got a tie, and that's to kind of contain the thrust that this kind of happens from the arching action. So it's actually quite a nice tool to kind of understand how the structure kind of wants to behave, and therefore if we do deviate from this, you know, what we kind of understand what the consequences might be. Here's another one. It's kind of very similar. We've got, but in this case, we've got structure kind of spanning diagonally. And the reason for this is because we've got relatively flat sides, which like to bend a lot, and we've got curvy corners, which are really stiff. So in this instance, the structure is really wanting to go to the stiff supports of the corners, and so it's added columns there as well. So you really get a lot of insight, which kind of helps you to think about where you might, even if you don't build something like this, where you might kind of put your biggest columns, your biggest members. And then we've got a ring beam, again, very similar to the last one, to contain the thrust from the roof. There are some different methods, layout optimization. Peregrine is a Grasshopper plugin that does that. Simp in the middle, and then kind of automated beam sizing gives you kind of similar ideas as well. And then just my final one is Nelda-Mead, or also known as the downhill simplex method. So this is a gradient-free numerical optimization method. So you will all be familiar with Galapagos, which is a genetic algorithm. Nelda-Mead is similar but different. So I'll just kind of go through that. So the reason that kind of I looked into the Nelda-Mead method is because genetic algorithms are great, but there's kind of every problem has like a kind of different requirement. So in some cases, what you really want to minimize is the amount of iterations. If I'm doing a finite element analysis that takes a minute to solve, I can't afford to have 800 iterations to optimize a structure, because it's going to take me 800 minutes. So maybe something like 63, the Nelda-Mead on the right, 63 minutes is maybe more acceptable for an optimization. But obviously this is a very kind of simple setup here, where we're trying to get from the high bits down to the low bits, and structure is a lot more complicated than that. So just very quickly, how this kind of works is we have a starting point, and we want to get to an optimum up there. So the way Nelda-Mead works is that this is in kind of 2D space. So we start with a simplex, which is made of 3 points, because we're 2D, we go with 3 points, we just need one more, and that kind of gives the algorithm an idea of which direction to go, because it's got kind of arms in different directions, so it can kind of feel which way to go. We know the worst point and the best point, and it kind of moves in the direction based on the worst and the best points, using different methods, either reflection or expansion. If reflection looks like a good direction, it tries expansion to go a little bit further. Maybe it wasn't quite as good. So there's these kind of different methods that it kind of moves about to kind of explore, depending on how good the values it gets from moving around in space. So this is kind of how it kind of moves in 2D, a way to kind of understand how it gets from the blue to the red, where X and Y are the kind of input parameters. Obviously, this isn't the kind of problem that we're looking to solve, but you'll see some examples in a sec. So we implemented this, and we've got a plugin in Grasshopper for this. And here's a kind of quick example. This is a structure that I showed briefly before. In this case, where our input parameters, instead of X and Y coordinates in space, our input parameters are the vertical position of the control points of our surface here. So we're kind of moving the surface, and then we send this into a structural analysis program from Grasshopper. It spits out our stresses, our deflections, and we kind of see how good a structure it is by moving these kind of points up and down, and we're moving the colored points together so that we don't get weird asymmetry. So here are kind of some of the solutions that came out. We've got kind of 2 local optima. We find those by restarting a new positions. So we've got our baseline in the middle, where you need a very big fabricated hollow section, and then for the kind of local optima either side, we've got some different aesthetics with some different sizes, much smaller steelwork. So that was one example, and second example relates to glass. So here's the two kind of methods of shaping glass. Every architect wants funky shapes of glass. The top one is slumping, which is quite expensive, requires more energy and has other limitations, but you can get all sorts of freeform geometry. Bottom one, a lot cheaper, lower energy, and also we can use coatings with a better performance, which is better for the environment as well. Limitation is it's cylindrical or flat only. So our other use for Nelda Mead was to kind of take objects, glass panels, and see what cylinder they might fit best to. So we've got a script on the left with our cylinder fitting algorithm. This time our Nelda Mead is embedded inside our C# component, so there's no kind of Galapagos kind of interface. And we've got our panels on the right, and they kind of spit out the optimal kind of cylinders for them by kind of moving around these cylinders and finding an optimum. So we can look at the deviations, the original curvatures, and the rationalized curvatures, and kind of check whether these deviations are acceptable or not. We did this on a project to Taikoo Place in Hong Kong. The architects originally were going for conical, which isn't the same as cylindrical, so we kind of optimized, found our best cylindrical representation of those conical panels and replaced them with conical panels with minimal visual effect, but now making it a lot cheaper and allowing the coatings that were required to be applied to the facade with a better energy performance. Here's a spur bank in Moscow where we extended these capabilities, now looking at kind of organizing the panels into flat, cylindrical, cold bent, slumped, and this required a little bit more analysis of the stresses. So we'll take in our models, going into finite element analysis, looking at the stresses and taking them back again. And then finally, I just wanted to, because I know I'm short on time, touch on NURBS, which is kind of work in progress, something I'm interested in at the moment, but want to spend some more time looking at. Obviously, like Rhino started out as it was all about NURBS. That's kind of how it started, I think, as a AutoCAD plugin to deal with NURBS. But I only realized kind of how cool NURBS were more recently with kind of isogeometric analysis. That's kind of a new thing that's come kind of in the last few years, at least from what I've seen. Kiwi is an example. But I think there's kind of more potential for NURBS. What I've been looking at specifically is kind of so NURBS is basically the mathematics of the structure, and you can kind of derive all sorts of things like developability and stuff, and this will give potential to kind of optimize freeform structures in a lot better way than we can do with meshes. So I've kind of dabbled in this a little bit, and really what I'd like to see, hopefully, maybe I'll end up doing it, or if not, you know, if someone else could do it, that'd be great. Having like a goals NURBS stuck into Kangaroo here, that would be great. So I know that Daniel Pike has kind of now enabled us to program our own goals, which is, I think, a great idea. So, you know, if we could do this with NURBS and free us from the meshes, then that would be great. So that's kind of something I'm looking forward to looking into a little bit further. So that's me. Thank you.
Great. Thank you very much, Sam. There's a nice note from Daniel Piker, who's watching your presentation, Sam, who said, definitely get in touch, please.
Okay,
So
will do.
you get some instant feedback there.
Great.
So please, anyone, questions for Sam, please type away those questions. But perhaps, yeah, Clemens, please. Your mic.
Thank you very much for the great presentation. It was super interesting. I have a few questions actually. This K-means algorithm, super interesting. Did you apply it also to like connection design? Because this has really, of course, a huge potential to limit the number of different connections and so on. And
like the physical nodes themselves, you mean?
Yeah, for example, if you think of steel connections, these are normally quite complicated.
Yeah.
I wonder whether there is a certain limitation on the number of dimensions that makes sense to.
No, not. I mean, in theory, there's no limit on how many dimensions you can go. I don't know if practically it kind of starts to break down at some point. I'm not really sure. I haven't looked into that. I haven't personally looked at node geometry, but I've kind of read a little bit about it and kind of thought a little bit about it, looked at presentations and that kind of thing. And it is quite a complicated thing to kind of, you know, again, it's about how do you measure distances between two nodes. You've got to formulate the maths to kind of compare two things. I mean, again, it's a question of why as well, because we did start kind of thinking about this for the cruise ship project, but then the contractor was like, well, I'm just going to mill all of my nodes, and so it doesn't matter if they're all unique, all kind of really complicated and twisty. I'm just going to get a lump of steel and mill it. So again, it comes down to, well, how are these things going to be fabricated? What are they going to look like? But there's definitely potential to do that with this kind of algorithm. Yeah.
Thanks.
Okay, a question from Alexander for you, Sam. Does your clustering node only work for triangular panels?
No, I touched on triangles because they were the easiest to explain, but you can do it with quadrilaterals. It just gets a little bit more complicated because even if all four sides are the same, one could be kind of skewed. So you've got to start looking at the diagonals and stuff like that. But yeah, it works for quadrilaterals as well.
Okay, and from Alexander again, can you please tell in an example from a kangaroo from, I guess, with clustering, which kangaroo nodes were used? Does that?
Yeah. So in this case, we're just kind of the definition of the similarities of the panels was about edge lengths. So we're basically using the kangaroo edge lengths to try and make them more similar to each other. So it's the edge length component, kangaroo component, that we're trying to get them closer to each other. So that was basically the gist of that.
Okay, another question for you. Could you please explain a little more about layout optimization?
You'll have to get the Peregrine guys on as a UGM, because I know very little, but I do know it sounds very clever. It's basically, rather than, so the topology optimization SIMP is like mesh based, whereas this is element based. So that's one difference, and it's a little bit cleverer than kind of throwing like Neldermead or Galapagos at it, because it uses the kind of stiffness matrices and stuff like that. So it's a much more mathematically kind of based approach. But yeah, ask the Peregrine guys.
Yeah, well, that's a good idea. Maybe we will have them present. Now, from Marcello, how do you consider the seismic load? And to add to that, do you use another program or only with Karamba?
In the SIMP topology optimization, I'm guessing. Yeah, so for the SIMP topology optimization, I'm feeding I'm using strand 7 as a structural solver in the background. So I've built everything up inside of Grasshopper and then kind of feeding it out to strand 7, collecting the results again, and kind of doing that iteratively. But there's no reason why you couldn't use Karamba. Karamba can deal with gravity loads, static loads that are going kind of sideways and stuff, which I think for this kind of iterative process, you want to keep it simple. You don't want to do crazy dynamic stuff because this is more kind of early stage optimization.
Thank you. Okay, again, question from Adelina. Did you write your own k-means algorithm or use one available from elsewhere? And also, what other applications do you see this used for?
So I kind of nabbed the starting point on a Grasshopper forum like many moons ago. Someone put something there and then I kind of adapted it. So that's the great thing about the communities, everyone kind of sharing things. There was a conversation on there years and years ago, and I adapted it because I needed to rotate my panels. I needed to be able to flip my panels and compare them that way. So yeah, half written myself.
Okay.
Yeah.
Okay. From Alexander again. Please tell us what criteria were used to optimize the weight dimensions for the nodal elements. The weight criteria was used, or some other parameters for production? Is that
not sure.
I might need to ask Alexander to reword the question.
Yeah.
Okay, Alexander, if you want to pose the question again, maybe in a slightly different way, I'm happy to try that again with Sam. So something else here from Ronaldo. Just how did you originally get into computational design, and what recommendations would you have for people that have joined us that are new to these subjects? So I guess Ronaldo's one of those.
I did a tiny bit of coding at university. That was MATLAB. I actually started off studying aeronautical engineering and then made the switch to structural engineering. So I got a tiny bit of coding in there. But other than that, it's just self-taught, diving into things. And Grasshopper's actually a really great kind of gateway drug to kind of more hardcore coding. Because it's so easy to get into, and it kind of gives you that logic that you need to kind of build on to get into other things like Python and C# and that kind of thing. And I think the best thing you can do is just go for it and just get stuck in. And there's no wrong project for kind of doing things like this. I don't think, no project's too simple. So just get stuck in.
Good advice. Okay. Now, from another question. Right, I start to see this trend of engineers, structural engineers, knowing how to code. Do you see this as a necessary skill to pick up? If so, would you recommend starting with C# or Python? If you had to choose, I suppose.
I picked C# because I had to pick something, and that was quite good for like building components for Grasshopper, for example. But do believe maybe you can do that with Python now, but you didn't used to be able to, at least. But I don't think it matters, to be honest, because the skills are transferable. Things like machine learning and those kind of things, that there's a lot of libraries and stuff in Python. So if machine learning, AI, that kind of thing is what you want to get into, then maybe Python is better. But just get stuck into one of them, and you can always learn the other one later.
Sure. Jeroen or Clemens, would you have a view on that?
Jeroen, do you want to start?
Actually, quite similar. I mean, this is an ongoing discussion and a never-ending discussion, right?
Yes.
It's people's favorites, but I tend to agree with Sam. Actually, once you get into it, it doesn't really matter anymore. Python is a great one, often to start with, as the syntax is a little bit easier to write. But personally, I'm a bigger fan of C#, let's say, for the same reason as Sam was saying. Like, yeah, that's where we started, and it was much more integrated within the Grasshopper. And then, it allows you to script within Grasshopper, within the script component. But then if you want to make the next step, as Sam says, to actually compiled components, you can do that still as well. It's very much transferable in C#.
I would also say C# is my favorite because there's one thing you have to define your variables, which you don't have to do in Python. And this sometimes causes the code to get quite messy if you're not very disciplined. But Python is very mighty because there are so many libraries available, and machine learning, matrix computation, and so on. So I would also say both of the languages are quite good. But for beginner, maybe C# is even easier. I don't know.
Okay, thanks. So one other question. Okay, have you got any other GH plugins or components for running algorithms, or are you developing your own, and are you developing your own, I suppose?
So the Nelda Mead one is on Food for Rhino. We put that one out there. Okay. But there's other kind of optimization algorithms as well by other people that work well. We write a lot of kind of code in house, but I think like it's one thing to write for yourself and make something that kind of does the job, and a different thing to make it kind of user friendly and UI being nice and stuff. And I'm sure Clemens knows all about that, and writing documentation and stuff. So I think you really have to have a good reason to delve into that. And as kind of consultants, it's I guess not something we necessarily have time to do.
Sure.
So I applaud those that do stick their stuff on Food for Rhino. It's great because there's a lot of work that goes into it.
Yes.
Okay, great. Thanks, Sam.
One question: the SIMP algorithm, did you code it yourself, or is it also some plugin, or?
Huh?
The SIMP algorithm, did you code it yourself, or?
Yeah. I mean, SIMP is an algorithm that there's many papers on, and I think Millipede is potentially a SIMP implementation. But yeah, I kind of coded my own so that it works with the Strand 7 finite element software that we have, that we like to use in house.
Cool patterns, really.
Hmm?
Very cool patterns that result from this.
Yes.
Okay, so is there any final questions within the group here, for Jeroen or Clemens for Sam? Otherwise, what we'll do now is just switch. So Jeroen, you can make your announcement, And then following that, we'll move straight on to Clemens's presentation. So I think now you'll have control of your, so we can see your screen, Jeroen, in a second, right?
That sounds great. Thank you very much. Actually, just a very short announcement. We're really excited to host our new next AEC Tech workshop hackathons and a set of presentations around it. Really a save the date announcement. So July 8th to the 12th, 2021, we'll host this. A lot of details still need to be finalized and figured out, but together with Grimshaw, KPF, and Simply Rhino, we're getting together and do this. In first instance, it will be virtual, let's say, but let's see how things develop from now until then, let's say. If we can actually meet in person, yes or no, then there might be some events either in our own studio in Thornton or with Grimshaw, both in Clerkenwell. But that's it, July 8th to 12th. So yeah, please stay in touch and we'll let you know more in advance.
Excellent. Thanks, Jeroen. Okay, so now we can go switch to Clemens and we'll get into Clemens' presentation and then we'll all meet again at the end. So see you in a while.
I have to get the right screen. So now you should see my screen. I hope it's the correct one.
Yes, looks good.
Yeah, first of all, thank you for having me, for the invitation. Yeah, I would like to present today a little bit about Karamba3D and about how it's applied in the office of Bollinger Grohmann, where I also work. Where we use it for, have used it for several projects now, and I will show 3 of those projects. Karamba was actually is actually a product of university research. Back in 2008, there was a research project at the University of Applied Arts in Vienna, which was about optimization of space trusses, and from there on, it developed, also in cooperation with Bollinger Grohmann, which is great because from there I get constant feedback, what could be improved and so on. However, it's now a thing on its own also. And there's a special thing about Karamba. I mean, it's a finite element program like many others, which are now around since the 1970s approximately. So since computers have gained access to engineering offices. The main difference to other finite element programs is that Karamba lives inside Grasshopper. So finite element calculations are usually connected with huge amounts of data which need to be passed around. And this makes this process quite sluggish sometimes if you have to export geometry from Grasshopper to some finite element package. And since Karamba lives inside Grasshopper, this bottleneck doesn't exist. And this was one of the things which we wanted to achieve, an interactive user interface, so that if you change something on the geometry, you immediately see also, do you actually see my screen? Oh, I think it's stuck now.
We can see your opening slide.
Sorry.
There we go.
Oh yeah. But yeah, this was the slide which I talked about. Sorry about this. That Karamba lives inside Grasshopper, and for some reason it's out of sync. Yeah, here you see that if you change something in the geometry setup, you can change the geometry, And this via Karamba, you see also the impact on the changed geometry or the loading of the structure on the structure itself. And since Grasshopper is a environment for doing geometry calculations, all the stuff which comes with structures like loads, supports, cross sections need to be supplied via Karamba. And since it's implemented in Grasshopper, you can also make use of the whole ecosystem. Like here, for example, there's a optimization done using Galapagos on a simple truss. With Karamba, you can by now calculate beam structures and also shell structures. There are several algorithms available, like buckling analysis, natural vibrations, cross-section optimization, BISO, so bidirectional evolutionary structural optimization, to optimize structures, because this was actually the first focus to use Karamba for structural optimization in the early design stage. This was where it was used first in the office of Preisinger. You get from a Karamba calculation graphical results like for many other programs, and you also get out the corresponding numbers, which is quite nice because this can then be used to inform, improve design, and thereby set up a feedback loop. In the meantime, there have been plugins around for Karamba, which can be used to export the data to other finite element software. And this is how it's done also in the office of Preisinger, that Karamba is used up to a certain stage, and for producing then documentation, reports and so on, and for doing a proof calculation, it's often the case that we move, for example, to RFEM or RStab or some other finite element program to do the final documentation. One thing which gets more and more is scripting with Karamba, and that's one of our aims to open up the software so that you can use Karamba in your own Python scripts or C# scripts. And in the meantime, there's now a unit test project available on GitHub which you can download, and API references. And when it comes to future developments, one thing which is new, that it's now also available on Shapediver. And of course, I want to implement more and more things to make it usable in different areas. The small things like line joints, or which has already been implemented, physical units, and result superposition and spectral analysis. Because at the moment, since Karamba is mainly used for structural optimization, there are some features missing which you would have in a normal finite element code. Because when it comes to optimization, it's often not necessary to calculate a very detailed mechanical response of the structure, but it's rather important to have a relative measurement between different alternatives of a geometry or a structure to make optimization work. And of course, there's also a GitHub page where you can constantly download the latest builds, and it's an open development insofar as feature requests can be posted or bug reports. And now I would like to turn to 3 projects. The first one is a dwelling house. It's called Mark's Active Energy Building. It was done by Falkes architects here in Vienna. And the building site is Vaduz, Liechtenstein. It's a small country near Austria. And the special thing about this project is that it has all the latest energy saving technology and solar panels and everything, so that it actually creates energy instead of consuming it. And Bollinger Grohmann was asked to do the optimization of the structure. And this is how the structure basically looks like. There are several floor slabs. There is a large wall at the back and an elevator shaft, which are there for the horizontal stiffening. And since this is not quite sufficient, there are also these V-shaped columns, which also provide some horizontal stiffness, and of course can also provide for vertical load takedown. And the question was where to place these columns. And for this, my colleague Robert Vielinger used Karamba. And the question was, how many columns do we need and where shall we place them? And here the Bezier procedure was used. There were regions in the floors where columns could be basically placed. You can see them here. These are the gray, dark gray areas. And so he set up a structural model, filled it with columns, placed the driving loads on it, dead weight and wind in this case. And then the Bezier procedure removes gradually elements which are not so much utilized. So in case of columns, a certain percentage of the columns with the smallest normal force get removed in each step. And then step by step, the number of columns is reduced. And what remains is then a pattern which shows how the forces flow through the structure. And in this case, you can see there are column trees which remain. And these are then, so this is the first approach to optimizing the columns. And Robert Vielinger also used a second approach. Then there's a second step, namely Galapagos. And he used Galapagos here to orientate the columns. And you can see that there's a relatively large gain at the beginning of the optimization, which gets then less and less. And this is how the structure looks like. The columns are prefabricated, so they have a very smooth and nice surface. However, the concrete in this case is rather a covering for fire protection. So actually it's more steel than concrete inside those columns. And this is how it looks like in real life. And so it comes quite close to the vision of the architect. And here a second project. It was done by Delogan Meisel architects. It's the so-called Hyundai Goyang Center. It's basically a flagship store of Hyundai Motors. So it's a big shop for selling cars. And the idea was to have a large open space underneath a roof, which floats above this space. And the roof is not only a roof, but also houses program. There are offices, there's a little garden there, cinemas, so quite some program. And so the first step here was to design a steel structure which conforms to the program. You can see here there are 4 reinforced concrete cores, which are there for the horizontal stiffness of the structure. And the span between those cores is approximately 50 meters, so quite large spans. And the question was how many additional columns are necessary. And of course, the architects, they wanted an open space, so no columns. But it's a question of cost also. My colleague Robert Villinger again, he set up this geometry here as a Karamba structural model, included again the governing loads, did a cross-section optimization, clustered also the cross sections, because it's of course not practical to have hundreds of different cross sections in such a project. And what he also did, he used Octopus to do a multi-objective optimization. The columns are actually not columns, but as you can see here, column clusters, which are like small woods of bamboo. And these the position and the number of these column clusters was parametrized and optimized using Octopus. And there were different goals, like the maximum displacement and the total mass of the structure. And the mass of the structure is a very good indicator of the cost. And the diagram here that you can see was done in a very laborious calculation. So there were done lots of optimization calculations. It took a very long time to actually compute this diagram. And what you can see is that if the displacements need to be small, then one needs to invest a lot of mass. For example, here for 5 clusters, there's the maximum here, and the more displacement that is allowed, the smaller than the mass that needs to be invested. So for 5 clusters, you have a rather extreme mass. For 6 clusters, it's getting better, and for 7, it's quite relaxed actually. And so this diagram was the guide for the architects, and they then from this diagram chose one alternative, which was then built, which was this one here. And another nice thing about having this model in Grasshopper was that the drawing of sketches could be automatized. And my colleagues, Moritz Heimrath and Adam Olinsky, they set up quite a large Grasshopper definition at that time. So the changes which the architects wanted to have were quite easy to accommodate. And so the sketches could be updated automatically. Today, we would rather use Revit for this task, but at that time, it was done using Grasshopper. You can see here how how the building site looked like, and yeah, it's now has been opened like 2 years ago, and yeah, it was a very nice project where Karamba was used up to the detailed design. And this one here is a rather smaller project in comparison. It's a pavilion, which was done together with Soma architects from Vienna. It's called White Noise. And this is the image which won the competition for the architects. What they wanted to achieve was the impression of randomness. That's also the reason why it's called White Noise. The dimensions are 20 meters by 50 meters approximately. And it consists of a large number of aluminum rods of a length of 2 meters. And it looks very random, but actually it is not, because the system consists of many layers of these rods, and they are all the position is defined via the membrane, which is on the inside. And what gives the randomness is the inclination of these rods. So this is one layer, this is the next, and the next. And the structural system works like this, where there are intersections between two layers. We have here connection studs. These are the black circles. And the inclination actually governs the way how the forces flow through the structure. So what the architects wanted to have was a structure which looks random, but at the same time stands up, of course, and has a good structural performance. And so my colleague Moritz Heimrath, he set up a Grasshopper definition. He used the geometry of the internal hull. There was a membrane which was for sun protection and rain protection. And he parametrized the model with this surface. And he split up the whole pavilion into 5 parts to make it work with Galapagos, because that's quite essential to reduce the number of free parameters, because the more parameters you have, the longer it takes to get to a reasonably good result. And the governing load cases were in this case the pre-stress of the membrane underneath the structure, at the same time wind, and of course dead weight. And using Galapagos, which allows to take account of only one objective, he had to put together a fitness number which took account of the maximum displacement, bending energy, which are both indicators of the stiffness of the structure, then the number of joints, which is an indicator of the cost, number of segments, and all from all of this, he set up a global fitness number, which was then used to do an optimization, which took approximately 1 night. And at the beginning, since the starting point is a completely random orientation of the rods, at the beginning the performance of the structure is very poor, but it gets better and better over time. And we certainly haven't found the global optimum, but it was a solution which was reasonably good, and this was fine for us and also for the architects. Since all of the parts were different, it was quite essential to have a digital workflow. So at that time we used Excel sheets to transfer the data to the workshop. And also it's very important to have a certain kind of order so that the right parts are there at the right time. And so you can see here how the structure was set up, put up layer by layer. And this is how it looked like on the day of the opening. It's I didn't mention this, but it's the main venue of the Salzburg Biennale, which is a festival which takes place every 2 years. So every 2 years, this pavilion is set up for like 3 weeks. And at the beginning, the Salzburg people, they didn't like it actually, because they're quite conservative. But maybe over time they will get used to it. Karamba is a team effort, and you can see the team members. And yeah, thank you for your attention, and would be glad to answer your questions.
Okay. Thank you so much, Clemens. Right, I'll just skip my screen. So a few questions for you and for the panel. First question from Andrew Phillips. Clemens, are you aware of any universities using Karamba as part of their core structural mechanics teaching?
Yeah, there are a few. University of Virginia, I mean, there are actually quite a few. So if I would now start to count them,
yeah,
like 20 to 30. I mean, most of the time, people write to me, and then I send over licenses for workshops and so on. So I would say over the past years, maybe 50 or so. It's hard to say, actually.
Well, I know Andrew. Andrew's at Imperial College, and perhaps we can get a list to Andrew separately if he'd like that. So we can come back to you on that, Andrew, as well, with a more complete list, I think. Okay, just a question for the panel, really, on their thoughts on this. So, do you think that there is a risk that students, I mean, I guess they're talking here about university students. The question has come from Andrew again. Is there any risk that students will fail or struggle at all to learn core theory if digital design is given more prominence? Now, I know, this isn't Andrew's thinking of, but it is something that we do hear, from, let's say, traditionalists. It'd be interesting to hear your views on that.
Well, I would say, I mean, there's the risk that people start to use these kind of tools as black boxes, so that they are not in the position of control, but rather get controlled by the tools. But I think they are, on the other hand, a great way to make things easier to grasp, because maybe if you think of interactive structural design, you see how the structure reacts, and thereby it's maybe easier to develop a certain kind of feeling for the structure, I would say. And also one learns to give a hierarchical structure to design, maybe, which is, I would say, sometimes helpful for architects.
Jeroen or Sam, would you have any?
Yeah,
Yeah.
I tend to agree, actually. Like it actually opens up more possibilities, I think, in a way of more options, quicker options, let's say. Yes, so the basics, they still need to come from the university curriculum, let's say, the base curriculum. But it just adds another layer to it, I feel. Like Clemens says, but also I really liked how Sam was talking about the DOME and actually the optimization algorithms, and how you can actually derive principles from it, but not necessarily directly use that as the answer, let's say. And I think that's probably the critical line where, one needs to be, in a way, right?
Yeah, I'd agree. I think, I guess there is the danger, but the same as with using finite element software rather than doing it by hand. It's the similar kind of analogy, but it obviously also offers opportunities as well. And I'd say that, like, I've had to revisit some of my university and school stuff by getting into kind of coding simp and stuff, and remembering what strain energy is, and trying to come up with a optimization algorithm, and remembering digging out my notes and understanding what virtual work is, and so there's principles you do have to understand, but you've always got to question what you're doing and why you're doing it. Like the clustering optimization, why are we doing this? Or do we actually need to do it, or are they just going to laser cut everything and it will be fine? So always kind of questioning what you're doing, and I think you'll be all right.
Okay, thanks for your answers. Okay, question from Mark for you, Clemens. How would you compare, Karamba to, the popular standalone FEA, products generally? And how would you position it?
Yeah, the unique thing about Karamba is the connection of geometry and structure, I would say, which you don't get in normal finite element software. I mean, they usually have their own geometry user interface, but and like COM interface also ways of how to interact with those. But this is something which was added later on, and yeah. The other thing is, of course, that most of the finite element packages that you can buy, the normal ones, they have, of course, more functionality. Like you can do printout reports, so that they're more geared towards the production steps that you have in a structural engineering office. And on the other hand, Karamba is more geared towards structural optimization, working at the interface of engineering and architecture. Yeah. So
I would say that because your Karamba is embedded so tightly with Grasshopper and Rhino, what most packages are really bad at doing is dealing with geometry, and it's such a pain to set up a model in most finite element software packages, and Rhino and Grasshopper do that really well. So you get that for free with Karamba, and that's what I think makes Karamba really powerful.
Yeah, and Clemens, have you seen evidence of this now that we're seeing the popularity of Rhino running inside Revit having an impact in more and more studios? Have you seen some, particularly with what Sam was saying there, the impact of that in not just perhaps in the Rhino environment, but within products like Revit now, that's potentially, or that is possible? Could you say anything about that?
Yeah, I mean, we use it now at the office of Polymer Roman, and it's a great way to interact with Revit, of course. I mean, I'm personally not a specialist in this data exchange things, but I think it's a great way to use Grasshopper to control an IFC model, so that people don't have to use Dynamo anymore, maybe. Or not.
Okay, thank you. Okay, a question from Sebastian. Is it possible to perform concrete design? Does it assist at all with this according to Euro codes with Karamba? Does Karamba help in that area at all?
Yeah, I mean, for shells, there's a reinforcement design procedure there, which is based on a procedure by Kaufman. So you get out reinforcement quantities based on a linear calculation of the cross-section forces. For beams, not yet, but I'm planning to have it as a feature so that you can at least do a linear elastic calculation and then do cross-section design based on cracked state. And let's see, maybe even non-linear, physically non-linear calculation. But that's still, I would say, a few months in the future. So at the moment, shells. Yeah.
Okay. And a question, I hope I can make sense of the question. This relates to the white noise structure. How did you analyze such a random structure with the described nodal joints?
Mm-hmm. The model was controlled by like 15 or 20 parameters. These were then used to create a spline, and from the spline, the angular values were derived for the individual elements because there were much more than these 14, and this was then how it was done. And the intersection was done using Grasshopper geometry calculations. So yeah, so for each set of parameters, there was always a feasible structure. This was the important thing.
You didn't have any collapsing flying structures or anything?
No, because maybe there were some, but there's always a problem with optimization engines like Galapagos, because if you have models which do not return a solution, then they can't be optimized. If there are too many of those, then the optimization normally doesn't work.
Yeah. And so you just did a set of 14, and then that was kind of duplicated. Is that
right? This was then blown up, and
yeah.
Because if you have too many parameters, then these genetic algorithms are then very time-consuming. That's an advantage, of course, of having something like Nelder-Mead. But yeah, I think it depends a little bit on the kind of problem, which algorithm is the best. And so for totally random, no, it wasn't actually totally random, but for structural optimization of this type, it's usually good to do it on with a genetic algorithm to avoid these local optima.
Okay. Well, I'm going to begin to wrap up. I just want to, of course, thank everybody for joining us, whatever time it is where you are. Please do, for future meetings, for keeping up to date with that, subscribe to our newsletters or follow us on any social media platform. I want to say thank you, of course, to our presenters. Thank you, Sam. Thank you, Clemens. Thank you, Jeroen, for joining us, helping out. I thought 2 great presentations, lively questions, so all very good. So just to remind everybody that it's being recorded. We hope to have the recording up maybe within a few days. And these meetings are all transcribed as well, so you see the full text there too, if anyone needs that. So we do have sponsors for these events, so I must just quickly thank them. The 2 sponsors there that I mentioned, Beam and PNY. Beam make a very nice, elegant tool for communicating between Rhino and Revit and vice versa. And PNY, who you may know, they are the distributors of some pretty powerful graphics cards from NVIDIA. So they help us with these events. So that's that. Finally, I want to just mention that our next meeting is on the 20th of May, and this will have a slightly sort of different focus. We're going back to our roots, you could say, with more of a pure Rhino story, with an industrial and automotive designer who has been a user of Rhino for many years. So hopefully that's of interest to some of you. You'll be welcome to join us again on the 20th of May. And I think probably the day after that, in June, we're going to be returning to another Grasshopper story, perhaps with an architectural flavor next time. I think that's everything. What have I forgotten, Steph? I always forget something.
No, wow. I think you've got it all. There's been some other questions come in, so I just want to say that we'll get back to people about those. There's some questions there for Clemens particularly, so maybe I'll pass those on to Clemens afterwards, and we can email those people.
Okay, will do. So thanks again, everybody, and good night.
Thanks, everyone.
Thanks,
Thank you.
everybody.
Bye.
Bye-bye.
Bye.
Thank you. Bye.